Hello, welcome. My name is Kamil Szymanski. I'm a software developer, and this is a presentation entitled Reactive Web Services. I work at Pragmatic Coders, where I develop the D2C investment platform for the British market, and this is gonna be a live coding session dedicated to reactive web services, reactive services, generally to the reactive buzzword. However, I do not want to focus on the buzzword itself. I want to focus on what reactive implementations are bringing to the table, what kind of problems they are trying to solve, how they are trying to solve them, and what's really new behind this reactive buzzword. So I would like to strip it off of the magic that has grown around it, the mass. And since I'm the Java guy, this presentation, it would be hard to do it in pseudocode. So all the examples will be in Java on the Spring stack. However, if you have a different background, if you're running on some other stack, this should not be an issue as long as you know any object-oriented language. If you know the basics of dependency injection, then you should be able to easily follow that. I've tried my best to keep the examples as simple as possible, yet as expressive as needed, so that I will be able to discuss those aspects related to reactive implementations that I want to talk about. And this is the last slide, so let's get rid of that. And let's get started. We will start with something completely not reactive, something that I hope we're already familiar with. This is a plain, old, boring MVC-style web application, web service. It exposes just one endpoint. That endpoint listens on GET requests, and once this endpoint is being hit, it executes a bit of logic. This logic basically performs an I/O operation simulated by this sleep. Treat it as, for example, a database call, calling a downstream web service, reading data from file, basically any I/O operation. And after that, we return to user what the I/O returned. It will be 42 in our case, but it doesn't matter. What matters here for the sake of example is that this I/O operation always lasts for 1 second. So there's no caching involved, operating system is not helping us, none of such stories. So keeping that in mind, I will have a couple of questions to you. So first of all, knowing that this I/O operation lasts for 1 second, what will be the perceived latency from the client's perspective, from the perspective of the client of that service? What will be the latency of it? Yeah, more than one second, at least 1 second, because the I/O lasts 1 second. But let's check it. So it's a bit more than 1 second for the first call. If we hit it for the second and following, if we issue following requests, then it will get faster. The first request was slow because it was the first request ever to that application, so a couple of things needed to be bootstrapped in the infrastructure. And why am I telling you that? In this session, we will be running a couple of semi-benchmarks. And we won't be doing them really properly. We won't be warming up the application, the JVM. Those will be semi-benchmarks, really simple ones. So what I would like you to focus on is not the concrete values that we get here, but rather the rough values. So what kind of a value the results oscillate around. So here we can say that they oscillate around 1 second. So the latency is roughly 1 second. And knowing that, I have another question to you. So let's assume that we have 5 concurrent users trying to hit this service. And how many TPSs, transactions per second, can we achieve with 5 concurrent users hitting that service? Any guesses? Okay, you're ahead of time, but not a problem. But if you were to tell, like, assuming that there's no bottleneck there, you would probably say that it's 5 TPSs, because the latency is 1 second and we have 5 concurrent users. However, because we are good software engineers, we don't guess, we measure it. So let's do that. We will run Siege. Siege is a tool that, above all, allows us to run HTTP benchmarks. So we will be running Siege in benchmarking mode with 5 concurrent users, and each of those users will repeat all the requests 5 times just to have results that are a bit more trustworthy. So let's run this benchmark. And as you can see, the latency is more or less 1 second. And the value that is interesting to us is transaction rate. So we're close to 5 TPSs. And you already told me that there can be a bottleneck there. So if we raise the number of concurrent users to 16, we would expect to have 16 TPSs. But you can see that the latency is growing, and we were able to achieve only 8 TPSs, not 16. You've said that it's related to some kind of a threat pool limit, so my question to you would be, what threat pool it can be? So where this bottleneck can live? Yeah, so basically I've done something in the configuration. I've set a limit of worker threads, the threads that are basically accepting your connections, and since we are running on a Tomcat, which is to non-Java guys, basically an HTTP server that works in a thread per request model. So each request is being served by 1 thread. So if we remove this setting and restart the service, we should be able to achieve 16 TPSs. And let's check if we're able to do that. So the server is up. Let's rerun the benchmark. And looking at the latencies, we can see that things are more or less good. We're close to 16 TPSs. But we've set this limit for some reason. It doesn't matter right now. What matters is that we would like to be able to still keep up with those 16 TPSs, having this limit of 8 worker threads on our HTTP server. So how can we achieve that? Is there anything that we can do with this implementation? What route would you follow? So basically, the only way to do that is to move this logic, this blocking operation, to some other thread. And we're able to do that. In the Java world, it's possible since really long years. From the Servlet 3.1 specification, which introduced asynchronous processing capabilities. However, we also have great abstractions built on that, and I will be using Spring, so the only thing I have to do here is basically, instead of returning string or whatever any object I'm returning, is to wrap it in callable. and the Spring will take care of everything. So what it will do is basically move this logic to some other thread and use the servlet's asynchronous processing capabilities. And let's rerun our service. Let's check whether it works. And let's see if there's something missing in this implementation. So let the server start. Okay. In the meantime, do you see anything that you would want here to have or not? Okay, let's rerun the benchmark. Let's see if we are able to keep close to those 16 TPSs, and yeah, we are. And what we were able to achieve is to keep up with those 16 TPSs. However, we don't have the full control over where we are moving this execution. It's being moved to some thread pool managed by Spring, and of course we can configure it by using some SPI. However, it's done globally. And in typical application, this is not the way that you would want to go. You want to be able to control where this execution happens per flow. So is it possible to gain a bit more control over that? Of course it is. Let me show you one of the ways. And we can again do that by using some abstraction provided by Spring. And what we are doing here, we're creating a deferred result set, then we asynchronously, as soon as a completable feature that we are running asynchronously finishes, we set the result, and a lot of technicalities. Basically, what we have here is really lot noise, not a lot of signal. So the ratio of signal to noise is really low. So this is not something that we would like to have in our business applications, because it's super hard to tell what this piece of code is trying to achieve. What is the reason that we have written it there? It's super obvious what we are doing here, but the purpose, basically we have to dig through a lot of technicalities. So how can we improve this kind of this thing and still be able to control where the execution happens? So let me go back to our example with callables. Let me copy the code using the best practices. And we'll sprinkle this implementation with a bit of reactive magic. So instead of callable, we will be returning mono. Mono is a reactive component that basically said that underneath there can be one result or zero results. Basically, at some point in time, this mono should complete with a result, without a result, or with an error. So let's return mono from our service. We will do that using the callable, and let's run our service. Mono is part of the project Reactor, which is a project created by Pivotal, guys behind the Spring framework. However, if you know something else from reactive extensions, basically Eric's Java, for example, or on the .NET side, reactive extensions. Mono will be something similar to maybe or single. And let's see how far can we get with the performance of such a service. There's no limit on the thread pool that I have set in this application. So this should be blazingly fast, or as fast as 16 TPS, because there will be I/O involved under the hood. So let me run this benchmark once more. And we can see something strange happening here because the latency is going above the roof. So the results wouldn't be as good as we would expect them to be. Let's wait for the benchmark to finish, but you can tell that we are basically oscillating around 40 PSs. And why is it like that? So this is not a powerful machine that I'm using here. This is a laptop that I'm using for presentations only. It has 4 CPUs with hyper-threading. And we've achieved 40 PSs only because something changed under the hood. We started using the reactive HTTP components, and Spring Boot 2 that I'm using under the hood switches from thread per request model and using Tomcat to using Netty by default. And Netty is an asynchronous networking framework that runs on an event loop model. So what we have done here in this implementation, we've done something really stupid. We've blocked on the event loop threads. And we have done that because by default, none of the reactive implementations involves asynchronous execution. By default, all of the calls, besides flat maps and things like that, run on the same thread that you've executed them. However, the really game-changing thing here is how easy it is and how safe it is to move this execution to some other thread. So if you remember from our previous example, like if we wanted to control where the execution happens, we had to boil down into a lot of technicalities. And with reactive implementations, it's as simple as telling where to execute this code, and there are operators for that in almost every reactive streams implementation. And we can do that, for example, by using the subscribe on operator and providing a scheduler. To simplify things a lot, a scheduler is something like a thread pool on steroids. And all of those reactive implementations come with some predefined schedulers, like, for example, Elastic, which is okay for most of the I/O operations, which means that basically as many threads that we need, that many will be created. There's, for example, parallel pool that says that no more threads will be created than we have CPUs, or immediate, which basically means the same thread that started executing that piece of code. Of course, we can gain a bit more control by creating a thread pool based on executor service, and so on. So we get a lot of control over it. For the sake of presentation, let's keep it as simple as using the Elastic thread pool. Let's restart the service. Let's rerun the benchmark just to check whether we were able to achieve those 16 TPSs. But in the meantime, the most important thing is the ease of moving the execution that we want to move to some other thread by only executing the single line, this one line of code. So let's rerun the benchmark. Let's see if we're able to go near to 16 TPSs, and yeah, we are. Yeah, this is the first execution, so if we run it for the second time, this should be closer to 16. And yeah, it is. So summarizing these examples, the possibilities to achieve those 16 TPSs to be sort of reactive. Of course, I'm not talking about things related to resiliency and things like that here. However, those possibilities are there for really long years. What's changed here is how easy it is to use them and how safe it is. So the only new thing here is the ease of use, cool API, things like that. However, this is not the only thing that is really great about reactive implementations, because if that was the only thing, there wouldn't be so much buzz around it. So let me go to another example. Again, this will be a simple web application, a web service. This time it won't be returning a mono, it will be returning a flags, which is a reactive component that basically says that underneath there can be any number of results. So it can be 0 results, 1, 5, 500, an infinite stream of results. And what we are doing here, we're simulating fetching documents from some repository. If you want to, if you don't know Project Reactor, but you know RxJava or from the .NET Work reactive extensions, this is similar to Flowable or Observable. And what we're doing here, we're generating an event each second. We take first 9 of those events and map them to documents. And for the sake of the example, let's assume that those documents that we are generating are really huge. Let's say those are PDF documents that each weighs 1 gigabyte. So what consequences are there with such an implementation? Well, first of all, we need to, because we're serializing those documents into a JSON, we need to be able to keep the whole data set, all of those 9 documents each of 1 gigabyte, we need to be able to keep them in memory. So for single user, single client of this service, we need a heap of at least 9 gigabytes from the documents for the payload, plus, of course, a bit more heap for the application to keep it running. And if there would be more documents, the heap would have to be larger. If there would be more clients, again, this would need to be larger. The other thing is that we're delaying delivery of that payload to the client to the moment that the whole payload is ready. So in that case, we will have to wait at least 9 seconds to start sending data to client. And from the client perspective, there is also an issue, because the client will have to deserialize this payload. So he will also need to have heap at least of 9 gigabytes plus the amount of heap that is needed to keep the application running. And before we start changing this implementation a bit, let me show you how the usage of this service looks like from the client perspective. So let's run the service. And let's pretty print as well the payload. So we're issuing the query, and then we're waiting. And if it takes a long of time, there's a huge chance that the connection will time out. However, if like it didn't time out, we get the payload. And if in the meantime, server didn't crash with out-of-memory error, if we didn't crash with out-of-memory error on deserializing this payload, we're able to start processing it. And why is it like that? It's because we're serializing it as a JSON array. So this is a JSON array of documents, treated as 1 GB documents. And how we could improve the way this application works. So one of the ways is to change what we are serializing. It doesn't need any reactive serializers, so reactive JSON, JSON, or whatever you're using. Probably there isn't such a thing. The thing that needs to change is that instead of serializing one huge JSON document, we will start serializing each of the documents that we are generating. So let me change one thing here. I will change the media type of this, this payload that we are sending to the client. I will show you how it looks like from the client perspective, and then I will tell you what's happening under the hood. So let's call this application once more. And what's changing here? Yeah, stream of JSON. Let me format it a bit. The resolution isn't that great here. Okay, so let's hit it once more. And what's changed here is instead of one large document, we're sending an individually serialized documents. And what are the consequences of such change? First of all, the server doesn't need to fit the whole payload, the whole dataset into memory. So we need a heap of at least 1 GB for serializing the document plus the heap to run the application. The second really important thing is that we can deliver the first document as soon as it's loaded and serialized. So the client doesn't have to wait for the whole payload to be delivered. He can start processing the first document as soon as it's ready. And the third issue that we had was the need for the client to be able to feed the whole payload into memory. And this is solved to some extent. If the client is as fast or faster than the producer, basically the issue is long gone. However, if it's slower, then it needs to buffer the things that he wasn't able to process. So this is not fully solved. However, for that, we also have tricks that have been working for really long years. So let me then jump back to the implementation and tell you what's going on here. So this looks like a bit of magic, and actually there is a bit of clever work going under the hood. And this is part of the contract of Spring Framework, so a really cool abstraction built on top of those reactive implementations. And the contract goes like that. If we're returning the stream of JSON and the payload is flags of something, what would happen is as soon as any event document in our case is generated, then it will get individually serialized. The response buffer will get flashed. However, the connection won't be closed. So we serialize one document, we flash the response buffer, bytes starts flowing to the client can start working on them. However, the connection is being open as long as we don't serialize all the documents that we wanted to serialize. And this is pretty cool. However, again, this is not something new. Those tricks, I've been using them in 2010, I guess, with implementations roaming around Comet, Bayou. Of course, it was way harder than today. But the only thing that is really new here is the API or the contracts being provided by abstractions built on top of those reactive implementations. In terms of possibilities, again, it was possible for really long years. And having said that, on the client side, there is still an issue if the client is slower than the producer, then for sure, if you heard about reactive, you heard another buzzword, the back pressure. And what back pressure is? If you read blogs, then the most common definition is that the back pressure is a way for a client to signal the producer that it's too fast and he should slow down. It's a huge simplification, so we will use another definition. This will again be a bit of a simplified definition. The back pressure is a strategy of dealing with too fast producer. So one of those strategies would be to tell to producer that he has to slow down. The other might be the strategy of saying to producer that he should buffer all of the data that we were unable to keep with. The other would be to drop anything that we were unable to process, or to drop everything beside the last known event. And it would be really cool to be able to use that. However, we're working over HTTP protocol here. And in terms of HTTP 1.1, there's no possibility for such thing because this is a request response protocol. There's no duplex there. In terms of HTTP 2, there is a duplex there. However, I'm not aware of any implementation that allows you to do that at the moment. So to demonstrate the back pressure, we will use this time a standalone application, not a web application. And I will talk only about producer side today because we don't have enough time. Or if you're willing to stay a bit longer, I can show you the client side. However, as I was telling you, there is not only one party involved here. We have here two parties, the producer and the consumer, and there is some protocol between them. And if we are using the reactive components, like for example flags, they are able to support this back pressure out of the box. So let me tell you what this example is doing. What we have here is again a document repository. This repository returns a flags of documents, so a component that is able of supporting back pressure. And then we have a subscription which basically simulates some processing. We start with logging on word level, then we execute something for 1 second and log the finish of this processing after 1 second on info level. Those logging statements are only for IDE to make a colorful output. And we have there nine documents. So let me run this application. I will make the output a bit bigger. And what's happening there, we start processing one document. After 1 second, we finish it. Then we start processing another. It's all happening on a single thread. on the main thread because first of all we haven't set the implementation to run on any other different thread, and the other reason is that that kind of subscriptions are single threaded by default. But in our case, this is something that we want, because what I would like to dig right now is the support of a repository for the back pressure. So having said that we are able to communicate to producer how much data we are able to process, I'd love to be able to get only that many data that I'm able to process at the time, and no more. So how can we check that? I have a simple test for that. It basically involves debugging. However, it isn't as hard as it sounds. What I do is I put two breakpoints. One is when we are fetching the data from the repository, and the second one is where the subscription happens. So let me run it through a debugger and show you what's going on there. So what I would like to have is on the subscriptions part to have loaded into memory only as much data as I'm able to process. So let's run it in the debugger. And what I do in the debugger is I open a memory view. And the first breakpoint is not that interesting. It's there only to capture the snapshot of what's on the heap. The more interesting is the second breakpoint, the breakpoint at the subscription level. So let me resume the processing, and let's see what we have on the heap. We are processing documents here, so let's check how many of them we have on the heap. And as you can see, there are 9 documents being loaded. So the whole data set is in memory, and I'm processing only a single document at the time. So basically, again, we have a similar issue. If those documents are large enough, we can run into problems like out-of-memory error. If we resume the processing, no more documents are being loaded because still we have the whole data set in memory. And we're gonna try to improve those things. However, before we do so, let's take a brief look at the implementation. So what we are doing here, we're returning a flux as a component that is capable of supporting this back pressure. However, we're creating this flux from data that is already loaded into memory, because we're creating a JPA query, and then we are getting the whole result lists. So it's not possible to basically load this document one by one, because the whole data set is already in the memory. And in terms of JPA 2.1, it's not possible because it was released before Java 8, so it has no notion of streams and things like that. However, JPA 2.2 will have a stream method that will allow you to open a stream. However, staying with what we have right now in terms of implementations, let's try to fix those things a bit. And to do so, we won't limit ourselves to JPA. We'll use the specific implementation, Hibernate in our case. And we will check whether anything changed. So let's run this application once more through the debugger. We will see whether things improved, and then we will talk what changed. So let the debugger start the application, connect to it. And again, the first breakpoint, it's not that interesting. We are just snapshotting what's on the heap. However, the second breakpoint is interesting to us. Let's look at how many documents we have loaded into memory. And there should be. Okay, let me resume processing. It should be easier at that point in time. We should see two documents loaded. And if we resume the processing, another document should. It's not documents, it's document. So sorry. Let me rerun it. I've searched for the wrong thing. So again, we're skipping the first breakpoint and we're looking at what's on the heap when we subscribe to the first document. And we can see one document on the heap, one got loaded. If we resume processing, so after 1 second we'll start processing the second document, we can see that the second was loaded. We have two documents on the heap. If we resume the processing, another document will get loaded. So basically we can load documents one by one. And at some point, garbage collector will be able to kick in and garbage collect all the documents that were already processed, which is not true to some extent. And this is not true because it will be able to garbage collect only the documents that are no longer being managed by Hibernate. So managed entities won't be able to be garbage collected because of dirty checking and stuff like that. However, the most important thing is that we were able to load only as much data as we were able to process. And the other important thing is how many queries were we executing to the database. So let me run this application once more, this time without debugging. And let's check how many Hibernate queries are we making. And here, is our application booting up, and there it's issuing the first call, which is basically selecting all the data that is in our database. And this is the last query that we are issuing. And this is, again, nothing new. Hibernate was able to do that for really long years. Plain JDBC also provided us with scrollable result sets. So the only thing here is, again, the API that allows us to achieve those things. So let's check the current implementation of the repository. And what we are doing here, we're again using the JPA Entity Manager. However, this time, as soon as we get grip over it, we unwrap it. We use the specific implementation, the Hibernate. And then, when we create a query, we open a stream over the results from this query, not over the result list that has been loaded into memory. This is something that will be part of the JPA 2.2. However, the most important thing is here under the return statement. So we're creating a flags over this stream, so we will be able to load as much data as we need and no more. And the other thing is that we are saying what to do on termination. So if we process all the documents, or if there is an error during the processing, we need to close the stream so that we don't leak resources, so that connections don't leak, things like that. However, as I've said, the GC won't be able to collect things that are already managed by Hibernate. So this poses an issue. And to solve that, we would have to lake a bit of abstraction. So for educational reasons, I want to show you how a plain JDBC-based repository implementation could look like, so that we would be able to garbage collect all the things that we need. So in plain JDBC, it could look like that we have a data source, we obtain the connection there, then we set auto-commit to false, only because we, for example, might want to open a cursor there and use that cursor, or some other capabilities of scrollable result set. Then we're creating and issuing a query. Okay, I hope this is readable. And then we're creating flags from an iterator that we will create over the result set returned by JDBC. And this result set is not the same thing as result list that we returned from Hibernate. This result set is not loaded into memory. Those are pointers to specific rows, to the next row in the result returned from the database. So let's see how can we create this iterable, or rather iterator, over the result set. So a Java iterator needs to implement two methods. One for checking whether there's a new result ready to be fetched, and other to fetch it. The has method to check whether we have more results there is as simple as checking whether there is a new element there, and if so, we return true. If there's none, there's an important bit that we have to close the connection. So again, we don't leak connections, and we return false. And returning the document is as simple as mapping data from the result set into our domain objects. So definitely not a rocket science. However, this is not something that can be easily generalized because there's no support for joins here. We're supporting only this one object. So this is a bit that we would have to implement per each case. However, still this is possible. So if we are suffering from loading too much payload in our applications, there are ways to do that. And again, this is nothing new. The only game changer here is the ease of doing that. We can do that by just creating a flags on top of the iterator that we've created. So this infrastructural bit is simplified to the great example, but it's not new. It's just a super cool API, and this is the part from of the producer side. Can anyone tell me how much time we have left? 7 minutes. So I can show you one of the things on the client side. So let me go back to our application. And this time we'll change a bit our subscription. We will use simple subscriber that I have written myself. Let me just run this application. And let me show you the scheduler. So this scheduler, it's doing a more or less similar thing. It's not doing it as a state of the art, but for educational reasons, this is a good implementation to try out things. So what we are doing here, as soon as we get the document, we are processing it, and we are processing it on some other thread pool. However, for now, let's get rid of that. So if we run this application, this should look pretty familiar to what we had previously. And there's not much back pressure enabled here. And it's not enabled here because we didn't ask for that. And we will stay on the side of telling producer only how much data we want to load at the time. So to do that, we will hook into one of the extension points. We'll hook on the subscribe method. And what this method does, it's being executed when we subscribe to the results, and the default implementation looks like that we are asking for as much for a really large value of requests. Actually, this is a special value. It's so-called unbounded value, which means you as a producer should give me as much data as you have. And that's why we're able to process things one by one. However, let's try to play a bit with that implementation. So instead of asking for all of those values, let us ask for only one value. Anyone can tell what would be the result if we run this application right now? So before, because we are not asking producer for all the values, we are asking only for a single document. Then instead of processing the whole data set, we will process only one document, and then basically we will be finished. So here you can see that only one document was processed. And how to fix that? Basically, to fix that, all that we need to do is to request for another document as soon as we're done with processing that. So this would be similar to asking for all the results from the producer. However, we're telling him to deliver it one by one, not relying on the things that this subscription is single-threaded. So here you can see that we're able to process all the data. And what possibilities that protocol gives us? We can implement more smart things. Like, for example, batch scheduler. What this batch scheduler could do is define a window so that we will be asking producer for a certain amount of documents batch by batch. So we can, for example, say to producer, give me batches of two documents. And then within that subscription, we can basically check whether we've processed all the documents in the batch, and if we have done so, we can request for another batch. And this is an implementation, again, only for educational reasons, because we shouldn't do things like that. We shouldn't do that because the existing reactive implementations come with really tons of operators that do exactly those things. So instead of rolling out our own implementation, we can reuse already battle-tested, battle-proven operators. So for example, Flux has a window operator that allows us to do so. Of course, it's a generic solution, so we would have to flat map over it. However, there's a really ton of operators to allow us to use those use cases. And this is something that we can use even if we don't want to parallelize our logic and stuff like that, only to have a more expressive API over what Java 8 streams already provide us with. And what's new here, again, this is a super cool, super expressive, relatively simple, relatively easy to use API. All the internals under the hood, basically those are things that are not new. Those are things that we know how to deal with from the 80s, 90s, or early 2000s. So to summarize it, reactive implementations are are a big step in terms of how expressive we can get with our implementations, how it makes supporting and maintaining code easier. Basically, this is the thing that we should focus on. Of course, there are things like back pressure support that is simplified to the huge extent. There are capabilities of resiliency, but those are things that were possible for really long years. And if you have any questions, I will happily answer them. I can see one on the slide here, which says why transaction time is below number of concurrent calls times 1 second. Whoever asked that question, can you tell me to what part of the presentation are you referring to? Or we can move it after the presentation. So, does anyone have any questions that I should answer? Or, yeah? Yep.
You were talking about, you were mentioning this little note, this stream JSON media type.
Yeah.
Does this work also when I don't use the Reactor project?
No, so this is part of the Spring 5 contract, and it says that you have to return a Flux, and also that you have to specify the certain media type. However, if you are using RxJava, for example, there are converters to do that. I don't know if they are they're in Spring already enabled. If they're not, it's super easy to do so. If they're enabled, this should be converted on the fly. So if you favor RxJava, basically you can work on that. Of course, you would have to have Project Reactor on the class path, but the translation is possible to happen without your intervention, like in the infrastructural layer. So on the client side, you're basically receiving JSON. So it's up to the client what how it will deserialize it. It should be able to understand this payload and deserialize it. However, this is nothing related to Project Reactor or RxJava. You can use whatever you have. And this stream of JSON is not the only media type that can be returned. There is also text event media type that will return the same data but wrapped as a server sent event. So if you are on the doing that for purposes of deserializing it on the web layer on the UI, it can return it as a server sent event. So it will be wrapped in JSON with data plus the payload. Okay, yeah?
You mentioned that there's no other backrush on the HTTP level, but I think there's a window size on TCP level. So, for example, HTTP, I think, can manage it.
Okay, so there is a bit of back pressure, like again from the 60s or 70s, like what TCP as a protocol provides us with. Basically the network stuff stack. However, this back pressure works on the networking level, not on the application level. So it can ask for another TCP packet, not for another document. Basically, if you have, basically you're limited to what TCP allows you to do. So you have to work on the packets, not on the on serialized JSONs on parts of the stream.